Hello maths fans, I'm Dr. Tom Crawford, a fellow in mathematics here at Robinson College at the University of Cambridge, and today we're going to be filming a mock undergraduate admissions interview in maths. As part of the admissions process at Cambridge, applicants will undergo a subject-based interview, which is usually around 20 to 30 minutes. The interview is entirely academic in nature and is designed to give us an insight into how you think about that particular subject. Usually there are 2 interviewers present, but for today it will just be me. Everything else should be as close to the real thing as possible. I'll be interviewing Josephine, who is a current Cambridge student who has very kindly volunteered to play the role of aspiring Cambridge applicant. Hi.
Hi.
So to start with, we're going to think about a problem involving dominoes.
Okay.
Now, you do not need to know anything about dominoes, other than they are, of course, rectangular.
Yeah.
And in particular, they are 2 times longer than they are tall. So their aspect ratio is 2 to 1. So for example, if this was 2x, then this one would be x. Other than that, it doesn't really matter what's going on. And the first problem we're going to think about, so let's say question 1, is suppose I have a chessboard. So this is going to be 8 by 8.
Okay.
So we have our 64. I will draw these. I'm going to draw them all, yeah, because I think this is important. So we've got our 64 squares, and they're going to alternate in the usual manner between black and white.
Okay. And we're not worried about the numbers on the dominoes or anything?
No.
Okay.
No. So again, I'll just shade a few of these in just to make it really clear what's going on. And you can choose to shade any others or not as you see fit. Cool. Now, if I were to take the domino, it's going to cover 2 squares.
Yes.
I'm glad we agree on that. So given the ratios and the sizes we talked about,
And
right?
this has the same...
Yes.
Yeah, the size of a square.
Let's say yes. It doesn't matter too much, but yeah, we can say it's the same size. So obviously we can fill the entire chessboard with dominoes.
Yes.
Again, I say obvious. I hope we agree, right?
Yeah.
So okay, simple question. How many dominoes would it take?
There are 64 squares, so 32 dominoes.
Exactly. So we would arrange them all, and we could put them in slightly different patterns. We don't have to have them all horizontal, but either way, we are both happy that could be done.
Yes.
Right. So now, what happens if I remove this corner square and this corner square from the chessboard? Can we now fill the chessboard with dominoes?
Okay. Can I...
Please do.
So I'm just going to fill in... just going to fill in this side.
Yeah, absolutely.
Just to look at the colours and where they fall.
Yep.
Okay. Okay, so this is a white square.
Yes.
And this is also a white square.
Yes.
And when you think about when the domino is placed, the domino has to cover 2 adjacent squares.
Yep.
So it has to cover a black square and a white square.
Yep.
And so when we covered the board the first time, for every black square, we also covered a white square.
Yep.
And now we have 2 white squares missing, and so we won't be able to cover it all because there'll be unbalance between the number of black squares and the number of white squares.
Perfect. Yeah, very good. Yeah, it's exactly that. So you can also think of it as like a parity, question of parity, if you like that particular word. Okay, perfect. So as you've said, it's because everyone's covering 1 black, 1 white. We've removed 2 white, so we've got 30 white, 32 black.
Yes.
It's not going to be possible, no matter how many diagrams you draw.
Yes.
Okay, brilliant, well done. Right, so question 2. We're still thinking about dominoes, but now we're interested in, well, I say dominoes. We're thinking about squares, actually, and then we'll come back to dominoes. And we're interested in how can we piece together 4 such squares. So a domino is made from 2 squares, as we've just discussed. And now if I were to add another 2 wherever I want, so I could put another 2 like this, and that creates one possible, we call it a tetronymo.
Okay.
And it is after the name Tetris.
Oh, okay.
Tetronymo.
Tetra for 4.
Exactly, meaning that we have the 4 squares. So this would be one possible combination of 4 squares.
Okay, yes.
What other combinations could we create
With 4 squares.
Yes, and what we're interested in here is where they are unique up to rotation. So I could rotate this square 4 times, 90 degrees each time, and you could argue that the squares are in different locations, but we're not interested in that. You know, if I were to number them 1, 2, 3, 4, and you rotated it, that's still the same shape.
Yes, I see. Yeah.
So up to a rotation, what other shapes could we create, and how many of them will there be?
And this isn't thinking about the dominoes, is this link?
No, this is kind of dominoes with 2 squares. We're now jumping up to 4 squares, tetronomos.
Okay. I think just straight off the bat, I'm going to start drawing some.
I think that's a great idea.
See what's going on. Okay. Do I just go like, oh, okay. So the first things first, I'm going to sort of take this square on this end and move it around. Keep everything else in the same spot.
Yeah.
And this square can either go here.
Yes.
Or it can go, or it can go here.
Yep.
And then I can think about moving. I'm sure there's a more optimal way of doing this, but I'm just gonna get some things written down.
Yep.
I'm gonna think about taking this one now, the second one, and I'll move it around to here. But this has now repeated
Yes.
this, so don't count that one.
Yeah,
Okay.
it's just a rotation of 90 degrees, exactly.
Yeah. Okay, I see. Okay. I guess we can think about it as having a sort of bigger grid and how many of those blocks in a bigger grid we can shade.
Yeah.
Kind of maybe for counting. Might be a bit better. But at the moment we've got 3. Okay. If I consider like say this size grid. Oh, we can also have just that.
Yes.
Okay, so actually we can think about it as how many blocks we have on our kind of bottom row, if that makes sense. So here we've got 2, here we've got 3, and here we've got 2 again.
Yep.
I might think about that. So there's 1 block with 4 on the bottom.
Yep.
And then for 3, we can either have, sorry, this is a bit messy, but we can either have 1 block here, or we can have 1 block here.
Yep.
And everything else is going to be the same with rotation, I think. Or actually, no, I lied. We can also have this one, because are those the same? No.
Right, so why not? You're correct. Why are they not the same?
They're a reflection there. If you rotated this round, it would be here.
Yes.
Yeah. Ooh, now that's messed up my diagram. But yeah. Okay.
Good.
And then for 2 on the bottom, we can have this one that we had before.
Yep.
We can have 2 above, and then we can have 2 to the side. And for much the same reason as this one. Actually, no, we can't then do that. That's the same shape. Because if I wrote, is it? No, this is a different shape. Okay, I think. Yes.
So what did you say you needed to go from this one to this one?
Reflects.
Right.
And this is a reflection again, so they're not the same shape.
Exactly, yes.
Okay, so I think that covers all the ones with 2 on the bottom. Because we always have to have a connection. We can either have 2 connections here, which is this one.
Yep.
We can just have 1. And then for 1 on the bottom, we're going to have, that's going to be covered by all of these, because there'll always have to be 1 kind of connection there. So I think I've written them all down.
Okay, so how many do we think? Maybe let's try and use the highlighter.
Yes.
Maybe you can highlight the final ones that go into your count that you think are different.
I take back my grid from before. Okay, so 1, 2, 3, 4, 5, 6, 7, 8.
I think you've done that one twice.
Oh, yes, I
It's
have.
that one, yeah.
Take that back. 7.
Good, that is correct. There are exactly
amazing.
7. Yeah, well
Okay.
done. So there are 7 different tetronomos. I gave you a bit of a clue. I don't know how much Tetris you play. They are the 7 pieces in a Tetris game.
Oh, no way.
Actually,
I did not know that.
Now you do. Okay, right, now we're going to kind of combine the 2 problems a little bit. So
Okay.
in the sense of we are still working with the tetronomos,
We're going to cover
and the
the
7.
chess.
Well, so we're not going to cover a standard chessboard
Okay, do you want to?
because it wouldn't be possible.
Ah, interesting.
But I'll let you think about why. What we're thinking here is we have 7 different shapes. So I'll set this up properly. So we have 7 different tetranomos. Okay. And what we would like to do is we want to fill, let's say, an n by n square. So a chessboard would be a 8 by 8 square.
Okay,
But this it could be smaller, bigger. It's up to you to figure that out.
Okay.
But we would like, so we can have the square of any size. We want to fill it with the tetranomos.
Okay.
But we're going to have one other rule, or the specific rule that must be true is where we use k of each type.
Okay.
So, for example, we have 7 different shapes. You might say, okay, well, what if k was 2? So you have 2 of all of them. Can you form a square?
Oh, okay.
What if k was 4? If I have 4 of all of them, can I form a square?
Okay. Yes.
So, but there's no limit on k. So you're allowed, so you have 2 variables. You're allowed to pick however many repeats of each one you want. But if you're going to have 3 of one type, you've got to have 3 of all of them.
Okay.
But at the same time, you can make the square as small or big as needed. So there's a
And
couple of
them
variables.
around,
You can rotate them around. That's completely allowed.
Okay.
Yes.
Yes.
So that's what we now like to think about. What is the what kind of squares could we maybe build, and what would be that value of k? How many of each type would we have for a specific size square? Some will be possible, some will not. That's what we want to think about and try and explore.
Okay. And because you said that the chessboard is not possible, I'm thinking it might have to be bigger or smaller. Yeah.
Well, if you wanted, I mean, it's clearly up to yourself. If you wanted to start by thinking about why the chessboard might not be possible, that could give you some insights, but feel free to approach it in your own way.
Okay. I'm gonna sort of go back and look at the dimensions of each of my points, because this first one here is a really, really nice one. That's gonna make, because it is a square.
Yes.
That's pretty nice. This one's pretty nice as well. It's when we reach these kind of ones with gaps that we sort of start to get into trouble. Think if we could start to sort of pair them up and have a look at when we can fill, like in Tetris, when we can fill the gaps. But all of them have a height of max 2. So we're gonna have to work with that. And these guys have a width of 3, and then these two have that. Okay, I'm thinking how I might pair them up, just to kind of get to grips with it.
Yep.
Yeah. Okay, so off the bat, these two here, sorry, this is getting very messy. Okay, these two here.
Yep.
You've got a gap of 2.
Yep.
These ones have a 2, have a forward part of 2. But I'm also thinking that if I put a square in here, that then I could put this up that, badly drawn, but take this one up there.
Yep.
But I'm not gonna do that right now. Okay, so if I take these ones like this, sorry, that, and then I consider what happens when I do what I said. Oh, this is kind of annoying. I might not put in the middle dashes, if that's all right, so I don't lose track of where I put my pieces.
Yep, no, that's fine.
Yeah. And then, okay, think about that. Okay. Okay. I guess when you look at this, you're kind of working with a combination of 3s on the bottom, 3s on the long, and then 2s on the long, and 1s on the long.
So we could, of course, because earlier when you were saying they were 2 or 3, we could, of course, rotate this one and be a 4 horizontal, or it could be a 4 vertical.
Yes. Yeah. Okay.
So there is actually quite a lot of
there's
freedom.
There's a lot of stuff going on.
Yeah, because again, if you rotate it, then you could also have a width of 1. So you could almost have a height or a width of 1, 2, 3, or 4.
Okay. Yeah. I see.
So there's quite a lot to think about.
Yes. Okay.
And it possibly, if you think about, it's not too dissimilar, let's say, to the chessboard and the dominoes.
Okay.
In certain ways.
With the colours.
Maybe.
Maybe.
But just in terms of, so let's say when I initially asked you that very first simple question of how many dominoes fill the chessboard. So rather than thinking about the
look at
shape,
all the squares.
what were we actually,
Okay.
it wasn't the shape you were concentrating on there,
It was what are they covering? Or
so the area.
yeah.
It was the fact that, right, so you told me that it was 32 would fill the 64 squares. We didn't care whether they were horizontal or vertical.
Okay.
Because it was just, you knew a domino was 2 squares. And we also happen to know these have different, more complicated shapes, but they're always
4 squares.
4 squares.
Okay.
So could you use that perhaps to try and get somewhere, let's say a starting point?
Yeah, I can write a little expression down. We're going to have 4... sorry, I'm just going to rub that. Okay, so for each, if we have k of each type, then we're going to have 4k times 7.
Yes.
Or number of total little squares.
Yes.
And that has to add up to n squared.
Yes.
Okay. And, okay. And so this is going to be 28k needs to be n squared, needs to be a square number, which means k has got to equal a number n squared times 28. If that makes sense. Because this, oh no, I take it back. 4 is a square. 4 is a square. 4 is a square, so it's got to be m squared times 7.
Yes.
Yes. And m can be 0, 1, integer. No. Yes. Integers are negative as well. So anyway. Okay, so if m is, no, m can't be 0. M could be 1, sorry.
It's all right.
The natural numbers.
If it was 0, you just have 0 of them all. You could argue it's the empty square.
You could make it a bit more complicated, or maybe a bit less complicated. Okay, so if we start off with m is 1,
Yeah.
and then we have 7 of each type, I no longer think I can draw that. But we don't know that they could all fit in that orientation, or do we?
So would it definitely work?
No, I don't think it would definitely work.
Okay, is there a possibility it would work?
Yes.
Okay, we can say it definitely...
It definitely maybe works.
we cannot say it won't work.
Yes. Okay. Yeah.
Right?
Yeah.
But you're right. We would still need to construct it, but it gives you a potential starting point. So maybe can you just explain that a little bit more? The process that got you to there.
Oh, okay.
Because we have a potential solution,
Yes.
which we'll explore more in a minute. But why do you think that's a potential solution?
Because this is the first solution where we have the actual number of squares.
Okay.
That would make a square on the board, if that makes sense. Everything else wouldn't fall of a square number of little squares.
So what?
Lots of squares.
Yes. How many would we have? Let's start with that.
Oh, okay.
So what would be the size of the square?
It would be 49 times 4, which is 296, I think.
196.
Oh, 196, yeah.
So that's our square number. So that means our square is what size?
It's 28 times 28.
14 by 14.
14 by 14.
It's okay. We prefer symbols to numbers. So it's not a problem. Right. So potentially, if I've understood your sort of, what I think you figured out here is you're saying if we had a 14 by 14 square,
Yeah.
we would have 14 by 14 board, chessboard. We have 196 squares.
Yes. Yeah.
If we then had 7 of each of our tetronymos, so 49 tetronymos in total,
Yes.
because we have 7 of each type, there are 7
Yes.
types, Each of them has 4 squares.
Yes.
That's 196 squares.
Yes, yes.
Right.
Yeah.
So it's a possible solution. And you're right, that would be the first, like the smallest one where the square numbers line up with
the number of squares.
the 4k times
Yeah.
7 that you figured out.
Okay, yeah.
So you could try and draw it. However, have we seen anything else that could help us where we didn't end up drawing it, but we could deduce something?
The colours on the chessboard. Okay. So if we've got, for each of these, we could just colour it like a chessboard with just one.
Yeah.
Yeah. So we'd have to cover, all of these would have to be adjacent black and white, like this, if we were on the chessboard. Okay. Just having a look. I mean, it doesn't matter. But, okay. Can we, like, line them up, or... okay. Well, okay. So each of these, I see. This is covering two blacks and 2 whites.
Yeah.
This is covering 2 blacks and 2 whites. This covering 2 blacks and 2 whites. They're all covering apart from this one, which isn't covering 2 blacks and 2 whites, which means 7 of these is going to cover a non-equal amount of blacks and whites. It's got 2 more whites than it has blacks, or vice versa, if that makes sense. And because then we have an odd number of rounds of all of these, we're going to have a non-equal number of blacks and white tiles, if that makes sense. And so it won't be able to cover the chessboard.
Okay. I think yes. Let's just unpick a little bit.
Yeah.
I think you're definitely onto something very promising.
Okay.
So let's just think about the blacks and the whites. So we know, again, working with the 7 of each potential solution. So given the ones you've drawn here, I guess, so first question then, this one down the bottom.
That could cover.
So it covers 2 blacks and 2 whites.
Yes.
You've drawn it one colouring. Is there another way it could be coloured?
Yes. This could be black and this could be black.
Right. But no matter how you colour it,
it's always going to have 2 of each. Yeah.
Right. Yeah. And I think this is kind of what you said about the other 5 of the other 6 were the same.
Yes.
So given we know we have 7 of them, let's keep a running total of blacks and whites.
Okay. So we've got 6 that have 2 each. So we're going to have 12 blacks and 12 whites so far.
Yes.
And then here we've got...
and that's multiplied by 7.
Oh, yeah.
Isn't it?
Redeeming myself with the mental maths. That was wrong.
7 times 12?
Oh my god. Oh my god. No, I'm not. Okay. Wow. Okay.
And we have no choice.
No, we don't have a choice.
Right. Because again, if we swap black and white on any of them...
This is symmetric in
doesn't
black
work.
and white.
Right, okay, cool. So how many of each are left? Blacks and whites.
From the whole...
the total of our 196 squares.
Okay. Oh my goodness. Okay. So we're left with 800 and no. Okay. We're left with. You know what? I'm actually going to write this whole thing out because I'm not even going to try doing it in my head anymore. Minus 2 times 84 equals 196 minus 168.
Yeah.
Which is, thank God, which is 28.
Yes.
Okay. And so we're left with 14 blacks and 14 whites.
Okay. And we have to have 7 of the T shape.
And the T shape is going to give us...
But we have 2 choices now, don't we?
Yes.
Because they don't all need to be 3 white, 1 black.
Yes. So we can have combinations of 1 black and 3 whites and 3 blacks and 1 white. And we have to have n of these and m of these. so that they equal 14 blacks and 14 whites.
And n plus m must be?
N plus m must be 7.
Yes, because we have to have 7 of the T shape.
Okay. So actually we can put that in. Can I? Oh, okay. That's useful. So I can just put this in here, like this. Kind of an awkward way of writing it, but anyway, I've committed now. 3b plus w.
Mm-hmm. Yep.
Okay, and this equals, we've got n minus 3n plus 21 blacks. Yes, okay. I lost all faith in my... And then 3n plus 7 minus n whites. Okay. Yeah, okay. And then this is going to be 21 minus n blacks plus 7 plus 2n whites. Yeah. And we want both of these to add up to 14. So we've got 14 equals 21 minus n equals 7 plus 2n. And so we want a number such that 21 minus n equals 7 plus 2n. Okay, and that gives 20, no it does not. That gives 14 equals 3n, which says that n is not a natural number, which is a contradiction.
So if we were allowed partial numbers, fractions, we could solve it, but of course we're not. Right, we want m and n to be integers, don't we?
Yes, we can't have 14 thirds of a tile. Yes.
Unfortunately not.
Yeah.
So annoyingly, that one's not going to work.
It doesn't work. But what could work? Is that what we're going to look at next?
Well, we're sort of coming towards the end, but just as a final thought, I guess, is there, thinking about perhaps why this one failed, and of course it being this T shape, is there something you could do? So we know that the 14 by 14 was really close to working.
Yes, yeah.
So is there sort of a case from there that maybe would work? Can you use that to build something a bit bigger that might work?
I think if we multiplied it by 2 and we had like 28 by 28, then we'd have an even number of these tiles.
Yep.
And so you could kind of think of it as for every 3 whites plus 1 black, you could get a 3 black plus 1 white, and then they'd have the same amount.
That's it. That's exactly it. Yeah.
Oh,
So a 28 by 28. So it would remove the problem of the T shape.
Yes.
Does it mean it's doable for 28 by 28?
We can go back to this, what we were doing originally.
Well, it fits here.
Yes, it does.
It definitely fits here.
Does it mean it's doable? I would say yeah. Or no. It eliminates this problem, but...
So if we think about the steps we've gone through, because we have done a lot here.
Yeah.
Thought about a lot of different things. So the first thing we thought about was, do the numbers work? So you were talking, had this great idea with the square numbers. We know that works.
Okay, yeah.
And remember, we said if the numbers don't work, we can say no.
Yeah.
But if the numbers worked, as we've seen, it doesn't necessarily guarantee a solution.
Yes. Yeah.
And then we did a similar thing. So we said, right, the numbers work for 14. Now we looked at parity.
Yeah, but we haven't looked at like where we're placing them or anything, and that could be the problem. So
right. So the numbers work, the parity works. So it's like it's satisfied like the minimum requirements to exist. But that's exactly that. We don't know yet until we draw it.
Okay.
So you would have to draw out a 28 by 2. Oh, come up with some other conditions.
I don't want to do that.
I think yes, I think it does work.
I was about to ask you if you actually...
I have yet to have the patience to draw a 28 by 28 square. So
and then
arrange
watching. Play a lot of Tetris, and then maybe you'll know.
Yeah. Okay, brilliant. Well, thank you very much.
Thank you. You can have your pen back.
So that is now the end of the mock interview. In the real setting, the candidate, Josephine here, would have the opportunity to ask any questions they might have, possibly about the course or maybe something we discussed. They would then be asked politely to leave, and then I would discuss the performance and the feedback with my interviewer. However, given we have Josephine here with us still, and this is a pretend mock situation, let's find out your first thoughts on how that was, because you didn't know the questions.
I didn't know the questions.
So I did not tell her the
promise.
question. We wanted this to be as realistic and representative as possible. So what did you think? What are your thoughts?
I thought they were good questions. I enjoyed doing them.
Yeah.
I feel slightly humbled by my mental arithmetic ability, but I promise it's better.
Well, on that point, because that seemed, I noticed as we were going through it, you seemed to be a little flustered, understandably, when, with those to me, very small, I don't care.
Yeah.
I'll be honest, it's great if my students, mathematicians, do not make sign errors, but we all do it.
Yeah.
Anyone who's watched my exam videos, I'm always forgetting minus signs. It happens. So for me, those kinds of things, I totally understand they can be very off-putting as a candidate and as a student, but for me, as the person doing the interview, I honestly don't care. So the more, so again, I wouldn't worry about that.
Okay. But yeah, when I went on to the second question, I felt it was quite a step up from the first one, and writing everything out was super, super useful. I think getting things out on the page, talking through what I might do, even if I didn't actually end up doing the grid method or something, but I thought it was good to sort of see everything in front of me. Yeah.
Yes, and drawing pictures.
Yes,
I like that you almost seemed a little bit questioning, oh, am I okay to draw pictures? But that's I think for a problem like this, it's so visual. So I was glad that you spotted that and you jumped in and tried to draw the things.
Thank you.
Okay, and overall, how did it?
Yeah.
Do you think it went well? From your perspective?
I hope so. Yeah, I think it went well. Yeah.
Yes, it did. It was very good. I will do more, let's say, formal feedback to the camera in just a moment. But I just wanted to give an opportunity for you to obviously feedback on how you found that, and how the viewers may have found it as well.
Okay. Thank you.
So as I just mentioned to Josephine, when we were getting her feedback there, from my perspective, I thought that was really good. As there is a reason Josephine is a current Cambridge student. Very much was demonstrating a lot of the problem-solving approaches, the logical thinking that this type of question is designed to test and is designed to give me a feel for, in terms of the applicant's aptitude for thinking like a mathematician. So to focus on, I guess, the questions specifically, the first one, obviously, very quick off the bat with spotting the idea about black and white, and sort of purposefully introducing that concept in the hope that we are going to see it again later in the question, is how I sort of planned that, as we saw in the last part. Then we got onto the drawing of the shapes, and again, it was good to see Josephine, taking the initiative and drawing pictures, because it's a very visual problem. It's based around drawing shapes, and so for me, it was really nice to see, that kind of experimenting, playful aspect in just trying a few things. What I also really liked in that section was when I sort of questioned Josephine and said, so why are these two different, or how do these two differ? And the fact that she was able to identify the rotation versus the reflection is a nice bit of sort of more advanced knowledge, perhaps, demonstrated in that particular problem. And then the last part, so we sort of got our tetronomos, we have our 7 different shapes, and now we're trying to fit them together in the square. So I think this actually worked really well as a demonstration of what a typical interview looks like, in the sense that there's a lot going on. There are multiple variables. There's a lot to get your head around. And so the initial idea that Josephine sort of tried to work through of fitting together those shapes and just trying to see what was happening. So some of you may have noticed we sort of did that for a few minutes. And then in my role as the interviewer, I'm sort of then, I've realized if we keep going down this path, we might end up spending way too much time, and it's possibly going to be a dead end. So my kind of role there as the interviewer was to just kind of steer us back towards what I know to be a more successful path towards the solution. And I sort of did that by saying, well, what did we do in the first question? So hopefully it was apparent that I wasn't saying try this, but as the interviewer, I'm sort of saying to the applicant, well, this is, we've tried this, it's not quite getting us somewhere. What else could we think about? Did we do something earlier that could help us? And sort of, that's a very, very minor nudge, but then I really liked the way that she then sort of ran with that, and then we went back and started to actually count the shapes. And as soon as she realized that we were just counting areas, very quickly and very comfortably could then write down the equation, very quickly could come up with the solution, was even working faster than me, to be honest, at that point, figuring out, m equals 1, we've got a 14 by 14 square, and sort of then going on from that point towards the solution. And again, the bit about mental arithmetic, I'm not bothered at all. That's not what we're testing here. The bit that was much more instructive for me in the interview was the way that that Josephine was manipulating those equations. So once we realized we had an equation involving b, w, and n, and also m, there's a lot of variables, but she had no hesitation creating those equations, solving them, realizing the solution wasn't a whole number, and then drawing a conclusion from that. So it was kind of, that was the bit that was impressive, and I think a really good demonstration of the mathematical skills that we're looking for, and that I was looking for in this type of question. So overall, as perhaps expected, given Josephine's a current student, I think a really nice demonstration of what an interview looks like, and also the key things that we're trying to pick out through this type of question. So that just leaves me to say thank you again to Josephine for being a willing volunteer to relive your Cambridge interview. A thank you to Robinson College and the AV team who very kindly filmed all of this. And a thank you to all of you for watching. If any of you do have any questions or you'd like more information about the admissions process at the University of Cambridge, or specifically questions about Robinson College, anything to do with maths or any other subject, we don't mind. Everything you need will go in the description box below. So put all of the links there, including also the Robinson College social media, which is excellent, and you should all follow that. So otherwise, thank you for watching, and I'll see you next time.